Hey folks, welcome to today's Luohan Webinar. So today we are super excited to introduce a new friend to you, Yunus Aybas, right? So Yunus is currently a PhD student in economic theory who is studying at the Stanford University at the Department of Economics. So today, Yunus is gonna bring a super exciting problem to us, which is about the chip talk in complex environments. For those who haven't known Yunus already, he is a microeconomic theorist, studying mainly the communication problems, the information problems, and also, how the structure of information environment is gonna impact your decision, choice, and outcome, as well as the welfare problems. So you can simply divide that part of research into the strategic and non-strategic parts. So for the strategic part, mainly about information design, and for the non-strategic part, probably you can think about the social learning happen on the social networks. So as usual, you're welcome to raise your questions throughout the talk. We will leave a few minutes in the end to accommodate, further discussions, but you are always welcome to raise them and bring the questions directly to the chat and conversations during the talk. And I am going to send a link in the chat for those who hope to have a copy of the paper in hand, as well as the slides. You can just click the link and download them from there. And without further ado, let's welcome Yunus.
Thank you. Very, very excited to be here and talk about my paper with Steve on cheap talk in complex environments. So today's talk, it's about expertise, and the expertise is very important. In many instances of real life, decision makers, they seek the advice of an expert who has better information about their options. In much of these encounters, what we see in real life is that experts often gain power over the decision makers. So some examples for this is that Milgram and Roberts, they studied division managers, and they show how they can manipulate the headquarters into funding too many projects. Another example is realtors convincing homeowners to sell too quickly and too cheaply. That's shown by Levitt and Syverson. And Gruber and Owings, they show that how OBGYNs can induce too many C-sections whenever they face negative income shocks. And more generally, for these markets for credence goods, where the seller has more information than the buyer, we see this phenomenon where they extract their expert power over the decision makers. In fact, Max Weber went as far as to say that the power position of an expert is always towering over the decision makers. Now, this is expertise in practice. What about expertise in economic models? Now, the canonical model that's used to think about direct and costless communication between an expert and a decision maker is the cheap talk model of Crawford and Sobel. That model has two key conclusions I want to highlight. First, communication is valuable. It makes everyone better off, but it has to be inefficient in equilibrium. Second, the expert in that model has no power at all. The outcome after the communication is exactly decision makers' ideal and expectation. In fact, when we look at these 2 points together, we can make the conclusion that the expert would be better off if she can transfer her expertise to the decision maker, because by this way, instead of getting the decision maker's ideal and expectation, they could have at least got that in realization and don't face any variance in their implementation. Now, this highlights something important. We have an enormous literature of applied models that builds on Crawford and Sobel. We use this framework to study how different parts of an organization communicate and coordinate, or how legislative bodies in a parliament gain power over the decision makers. But there's a big mismatch between models and practice, especially the fact that the experts in our models don't have any power. Now, let me try to explain you why with a simple example. Now, this simple example I'm going to show you, I'll be thinking about a doctor as an expert, and I'll be thinking about the patient's problem to get some treatment advice. Now, I'm going to think about treatments on the x-axis. These are different treatment options a patient has, but neither the patient nor the physician, they directly care about the treatments themselves. What they care about is the outcomes of these treatments. Now, for today's talk, I'm going to think about situations where physician and patient, they have different ideal outcomes. This difference in preferences, it can be due to the differences in the duration of the treatment, the pain level, the medication, the insurance payment, but I'll be focusing on the case where they have different ideal outcomes. To simplify this, I'll be thinking about patient's ideal normalized to this 0 outcome, and a physician trying to get an outcome as close to this red level. Now, let me first tell you how the classical models work and why they are going to end up with no expert power at all. Now, the canonical model of Crawford and Sobel, they start by assuming that the relation between treatments and outcomes is a linear relationship with a known slope. So both the patient and physician knows that the realized relation between treatment and outcome is one of these brown mappings with slope of -1. Now, the physician's informational advantage as an expert is the knowledge of the intercept of this mapping, which together with the commonly known slope helps him to identify the whole relation between treatment and outcomes, which means the patient, the doctor, the physician precisely know which mapping is realized. Now, in such an environment, suppose that the physician reveals a treatment that gives them their ideal outcome. So suppose that the physician reveals treatment R-star. Now, from this advice itself, what can the patient learn? Now, knowing that knowing that this recommendation is physician's ideal, and knowing the slope of the mapping, the patient can basically identify the realized mapping itself. So by learning the physician's ideal treatment, the patient can invert the mapping and learn its own ideal treatment in the classical model. And because of that reason per se, the physician cannot reveal their ideal treatment because then this information would be used against him. Now, in practice, the relationship between treatments and outcomes is highly unknown and complex in contrary to what's assumed in the classical models. So for example, the realized relationship could be this pink curve where R-star still gives physician their ideal, but the patient's ideal treatment is A1 star. Or the realized relation could be this brown curve where R-star is again the ideal treatment for the patient, for the physician, but the patient's ideal treatment is now A2 star. So if these two mappings are possible at the same time from the point of view of the patient, that means once the physician reveals that the ideal treatment is R star, the patient doesn't know whether they should pick A1 star, A2 star, or something else. So the broader message is in reality, the expertise is so complex that even if the physician reveals their ideal treatment, the patient still faces uncertainty about what's the best available action for them. So today, I'm going to talk about a model that precisely captures these real-life intricacies of expertise. That is, I'm going to introduce a strategic communication model in complex environments where this relationship is non-invertible. I'm going to do this by thinking about this relationship between action and outcomes as paths of Brownian motion. So in this modeling approach, the expert is going to know the whole realized path of Brownian motion, which means that the expert knows the outcome of every action. On the other hand, the decision maker knows that these paths are generated by a Brownian motion. This means that the decision maker knows the joint distribution of outcomes of each action. Now, in this model, I'm going to show you that the canonical predictions of Crawford and Sobel, they are completely reversed. The communication is going to be Pareto efficient. And in this equilibrium we identify, the expert is going to have full power. So the equilibrium outcome is going to be equivalent to full delegation where the decision-making rights are fully transferred to the expert. Now, this equilibrium, it captures the decision-making power of the expert that we see in real life. Moreover, this power comes purely from their informational advantage, unlike other models where we see experts having power because of their commitment power or institutions. Now, one question that needs to be answered is that, is this the right explanation? Do we really think that the experts have power purely from their informational advantage? Now, to answer that, I want to first go back to my medical expertise example and go back to the initial paper by Kenneth Arrow that started the modern literature of healthcare. In that paper, Arrow himself notes that as a consequence of the information equality, the patient must delegate to the physician much of his freedom of choice. So as Arrow identifies, our model identifies these large gaps in information as the source of expert power itself. In fact, this approach of using information as the main ingredient of power, it resonates with theories of power in sociology and social psychology as identified by Weber and French and Raven. Now, to this extent, I'm going to show you a result that shows how large of an information equality we need to support expert power by itself. Finally, before going in the model, I want to answer a question. Perhaps I'll let you start to ponder when I introduce the model. Why do we use Brownian motion? Now, the answer is a bit simple. It's a tractable model with attractive properties. What's this attractive property? It's precisely the ability to parameterize how much is learned from the expert's ideal action. We are going to use this parameterization to show how much learning from experts' ideal action is too much learning for supporting expert power. In a way, this is going to be our result about how much information equality is needed to support expert power. But what we do in the paper is that we show that Brownian motion and its special features, they are not really necessary for expert power. We provide lots of examples of other environments, and we extract the essential ingredient for expert power within these examples. So the essential ingredient for expert power for any of these models we use in the paper is a large information equality. By that, I mean that the expert in these complex environments can reveal their most preferred action while not eliminating all uncertainty. So after learning expert recommendation, in these environments, the decision maker still faces uncertainty. Okay, now let me jump into the model then. The way I'm going to do the rest of the talk is that I'm going to first introduce the Brownian motion model. Then I'll be jumping into the results. I'll first show a result about how decision makers would make a decision in this environment without the expert. Then I'm going to put the expert back in and show our main result about efficient cheap talk. And if time allows, in the last part of the talk, I plan to talk about how this result works beyond Brownian motion and why Brownian motion is just a single example of these environments. Now, let me introduce the model first. This is going to be a classical cheap talk model. So I'm going to have two players, sender and the expert. Sender, or I'm going to refer to as the expert, and the receiver, or I sometimes refer to as the decision maker. There are actions available to the receiver that takes value from a subset of the real line from 0 to Q. And the sender uses this message from this large set M to communicate. I'm going to do this intermediate step of defining outcomes before doing preferences for having this flexible model. So psi is going to be this mapping that maps every action to an outcome. And both the sender and receiver, they have preferences over the outcomes generated by actions. So the sender wants an outcome that's as close to this bias B. So they want an outcome that's closer to B. And the receiver, they want an outcome as close to 0. I'm going to use this classical quadratic preference with constant bias, what our results hold for weakly concave sender and receiver utilities. Now, the timeline of the game is that the sender is going to observe this mapping from actions to outcomes. So the sender is going to learn the outcome of every action, and then going to send a message, a recommendation to the decision maker, to the receiver. Receiver is going to observe this recommendation, update their beliefs, and then pick an action that maximizes their expected payoff. And then after that, the payoffs are going to realize. To wrap up the model, the solution concept I'll be using for solving this model is going to be perfect Bayesian equilibrium. Now, let me jump into the model with more pictures. Now, to remind, on the x-axis, I'll be thinking about these different actions available to the decision maker. On the y-axis, I'm going to have the outcomes of these actions. And I'll be thinking about the relation between actions and outcomes to be generated by a path of a Brownian motion. So this mapping itself, it's going to be our psi of A, and it's going to be given by a path of Brownian motion. That means if you take this action, the outcome is going to be the value of Brownian motion at that point. Now, the expert observes this whole realized map. They know the outcome of every single action. The decision maker, they don't know which mapping is realized. The realized mapping could be this green Brownian motion, it could be this pink Brownian motion, or it could be any other continuous function that we can plot here. What the decision maker knows is that this mapping itself, it's generated by a Brownian motion process. And the decision maker or the receiver also knows the parameters of this Brownian motion. So the first thing they know is that if they take this 0 action, the status quo action, the outcome is going to be psi of 0. The second thing they know is the drift of the Brownian motion, which means that they know the expected outcome of each of these actions are on this red dashed line. So starting from psi 0, the expected outcome of these Brownian motions, they change with rate mu. So this line is going to have a slope of mu. Third, they know the scale of the Brownian motion, which means that the variance of the Brownian motion, it grows at rate sigma squared. So that means as you get further away from this known status quo, the variance is going to grow. So I'm going to plot these one standard deviation away from the expectation with these orange lines. So if you take this action, you expect a standard deviation of sigma times A. So the standard deviation or the variance is going to go farther away. You go from a known point. Now, all that, it means that we can think about receivers' beliefs about the outcome of action A as a jointly normal distribution with mean psi 0 plus mu A and variance sigma squared A and the specific covariance structure. Now, today I'm going to talk about Brownian motion, which imposes this covariance structure. But you can think of this model in a richer way in the space of Gaussian processes, where we keep this joint normality the same, but change the covariance between different outcomes of different actions. The key property that the Brownian motion has that the standard models don't have is that learning one point in the mapping, such as learning the outcome of this point, learning this blue point, it's not equal to learning the whole mapping. So if the receiver comes up, gets some information that this point generates this action generates this outcome given by the blue point, their beliefs between the known point and this, the expectation is going to be given by the line connecting them. And the variance is going to be smaller in the corners that are closer to the known points, and it's going to grow in the middle. And to the right, the beliefs are going to follow the same drift. They are going to follow the same same rate of change in the expectation, and the variance is going to grow at the same rate. But most importantly, learning this point, it's not going to reveal the realized mapping. The decision maker still is uncertain whether the pink mapping is realized or the green one. Now, if there are no questions, I'm going to now talk about how a decision maker would make a choice in these environments. Okay. Now, in these environments, decisions without any further information by the expert, it's going to involve a trade-off between risk and return. Now, so is there... So decisions in this environment is going to involve a trade-off between risk and return. Now, taking action A to the right of this known point 0, it's going to improve the outcome by mu of A, because the receiver, they want to take an action that creates an outcome as close to 0. Now, taking an action A to the right of 0, it's going to improve the expectation by mu times A. But at the same time, the farther away you go from this known point, the more variance you face. The variance is now sigma squared A for taking action A. So that's why the decisions are going to involve this trade-off between risk and return. Now, to think about their ratio, or how hard it is to, how fast the variance grows, or how fast the expectation changes, I'm going to define half of their ratio. So sigma squared A over mu times A, and I'm going to divide by 2 to simplify, as the risk complexity of the environment. So alpha is going to be sigma squared over 2 times absolute value of 2 mu. Now, this ratio, it's going to parameterize our decision in a way. So our first result, it shows that if this risk complexity alpha is below the status quo outcome, then the receiver is going to make a choice such that the choice is going to have an expected outcome of alpha. So you are going to start at the known point, you are going to follow the drift line, and you're going to take this action that gives you alpha on expectation. In realization, it's going to give you it might give you something different, but from the point of the receiver, their choice is to pick an alpha that gives them on expectation alpha. Now, this means that if the status quo is bad enough, then it's optimal to pick an action that gives you alpha. Now, on the other hand, if the status quo is good, so if psi 0 is below alpha, then the optimal thing is to take action 0 and get psi 0 for certain. So that means if getting psi 0, if the certain outcome is good enough compared to risk complexity, it's good to take the certain action giving you the certain outcome. And if the status quo outcome is bad enough, then it's optimal to experiment with an action such that it will give you alpha on expectation. Now, in the rest of the talk, I'm going to use this result about decision-making without the expert when I'm thinking about how the decision maker is going to respond to a recommendation. Okay, now, the second part is that now I introduce the expert back into the game. So just to remind you, the sender observes this whole mapping, whole relation between actions and outcome, and is going to make a recommendation. And the receiver is going to now see this recommendation and then make a choice. Now, the question I'm trying to answer in this part is, how much power does the sender have over the final decision? And what I'll be showing is that the sender has full power if she can reveal her ideal action while keeping the receiver uncertain enough. So in order to study this, let me introduce a specific strategy for the sender. I'm going to call this the first point strategy. So what the first point strategy is that sender looks at the path of the Brownian motion, and the sender is going to recommend the smallest of their optimal actions. So she might have multiple actions that can give them the highest payoff. She's going to recommend the smallest. Now, I'm going to call an equilibrium a first point equilibrium if the sender uses the first point strategy and the receiver accepts it. Now, in any of these equilibria, sender's incentive compatibility, it's going to be immediate. Why? Because the sender is already recommending their optimal action, the best possible action they can implement. So there is no reason why the sender would deviate if that action is implemented in equilibrium. The question is, if the sender is recommending their ideal action, why would the receiver follow it? Why receiver's incentive compatibility would be satisfied? Now that's going to be more subtle, and that's going to require us to think about what does the receiver would learn from the recommendation about the path when the recommendation is made through this first point strategy. Now, in the next 10 minutes, I'm going to study this by considering the set of all paths that lead to this recommendation R star. I'm going to split them into two cases. Now, one set of paths that would lead to recommendation R star is if the realized path of the Brownian motion is giving the decision maker, giving the expert precisely their ideal outcome at R star. So if at R star, the recommendation is giving outcome B, then it's the optimal action. So I'm going to call then it's going to be optimal for decision maker, the expert to recommend R star. I'm going to call this class of paths event equals to B. These are events in the set of possible realizations of the Brownian paths. Now, in event equals to B, basically, I think about cases where recommendation R star has outcome B. Now, the expert observes this path, makes this recommendation of an R star. Now, the decision maker doesn't observe this path. And now the question I ask is that if the decision maker knows that the realized path is in event B, event equals to B, what do they learn? So I'm trying to make this exercise of thinking about the point of the receiver, what's their beliefs, conditional on the path being a path in event equals to B. What do they learn? Now, the first thing they learn is that R star is the first minimum. That means R star, it gives outcome B, and there couldn't be anything to the left that gives B or something below. Why? If there were to be any other action that leads to outcome B or something below, that means there had been another point where we hit B, so we get our ideal outcome, and it's a smaller action than R star. So the first point strategy would have recommended that one instead of R star. So by conditioning on event equals to B, they learned that R star is the first minimum. So everything to the left, they need to be higher than B. Now, the second question is, do they learn anything about right of the recommendation R star? The answer is no, because once you hit B at R star, once the outcome is B at R star, the paths to the right, they can take any shape. So they could be they could continue like this green curve, or they could continue like this pink curve. But no matter how they continue, how those paths are, what those paths are, the recommendation is still going to be R star, because R star gives the optimal action, and it's going to be always smaller than anything to the right. So that means there is no information contained in this recommendation to the right of the recommendation. So the beliefs to the right from R star, they are going to follow the same slope. The expectation is going to change at the same rate, mu. I'm going to call these type of beliefs neutral. So that means if we condition an event equals to B, my beliefs to the right, they follow the same rate of change for expectation and the variance. Now, importantly, there is another set of paths where the recommendation R star would be made by the expert. That's the case when the realized path attains a minimum at R star, and this minimum is above B. So if the realized path is this brown curve, the best possible action for the expert is R star, because it's the point that's closest to B. Now, I'm going to call these sets call these paths as event greater than B. Now, condition, so the expert observed these paths and make this recommendation. And now I'm going to make the same exercise. So if we condition on event greater than B, what would the decision maker learn from the recommendation? Now, the first thing they will learn is that there cannot be anything better to the left. R star is again a first minimum. Why? Because if the path were to go below this level to the left of the recommendation, that means there's a point that gives them a better outcome compared to R star. So then the expert wouldn't have made this recommendation. So the first thing the decision maker learns from the recommendation is that there is nothing below R star, nothing below the outcome of R star to the left. But now, differently from event equals to B, they also learn that at R star is also the last minimum. By that, I mean there is nothing to the right that gives them a better payoff compared to R star. The path is always above its current level to the right. More precisely, this means that beliefs to the right, they follow what they call a Brownian meander process. The Brownian motion is conditioned to stay above its current level to the right. This means the beliefs to the right, they are no longer neutral. We are conditioning this path to stay above its current level. In the paper, we characterize the moments of the distribution for these processes. And basically what we show is that the expectation to the right, it's going to follow this concave curve with an infinite derivative at 0, and it's going to be growing as we go to the right. Now, in reality, what's going to happen in the model is that expert is going to make this recommendation R star. It's going to reveal that this is the sender's optimal action. But the receiver wouldn't know whether the realized path is in event greater than B or event equals to B. So observing the recommendation, the receiver is going to form posterior over these events. What's the probability of this recommendation is coming from event greater than B? And what's the probability that this recommendation is coming from event equals to B? So we are going to think about, given a recommendation, what's the probability that we are at this case and we are at this case? So to study this, we study a new identity in the paper, which is the joint distribution of heating time and the location of the minimum. And using that, we identify a closed form analytic function that describes this distribution. Now, I'm going to use that to get to our main theorem. So our main theorem, it's going to state that the first point equilibrium, it's going to exist under two cases. First, if the misalignment B, the gap between the experts and the decision makers' ideal points, if it's small compared to the risk complexity, then the first point equilibrium, it exists for any game, basically, any complex environment chip top game that I described. Now, if the misalignment is larger than alpha, so if B is greater than alpha, then what we are going to show is that the first point equilibrium exists if the size of the action space is bounded from above by Q max B. Now, let me first show you the proof for the first part, that the equilibrium exists when the misalignment is small compared to risk complexity. So if when B is smaller than alpha. Now, the logic of the proof is the following. Now, if we are at event greater than B, if the realized path is this brown path, either case, receiver and sender have aligned action preferences. So if once the recommendation is made, conditional on event greater than B, there is no incentive to deviate. Now, if we are at event equals to B, receiver and sender, they have misaligned action preferences. Now, the receiver knows that there are better actions to they think there are better actions to the right, and they know that if they look for it, they might find something better. But now, this is precisely where the logic of the no expert result we established comes into play. What we showed was that getting an outcome for certain is better than deviating if that outcome is below alpha. Now, that means if I'm getting B for certain, I don't want to deviate, because if I deviate, I cannot get something better than B, because B is already below alpha. So using that logic, E in event equals to B, the decision maker also doesn't want to deviate. The risk of trying an alternative, it's basically too much compared to getting B for certain. So that means when the bias is small, you don't want to experiment when you're at the case where you have misaligned action preferences. And when you have aligned action preferences, you already don't want to, there are no better options basically. So this is the simple case. Now, what happens when B is larger than alpha? It's going to just follow, let's just apply the same logic. In event greater than B, we don't want to deviate. Now, in event equals to B, we want to deviate, right? Because getting B for certain, now B is above alpha, it's worse than alpha. Our result tells us that if we know that we're at event equals to B for certain, we want to deviate in a way that we get alpha on expectation. So we would have followed this red dashed line and take action A star that gives us alpha in expectation. Now, our result, it requires us that, okay, in event equals to B, you want to pick this action A star. Event greater than B, you want to pick R star. And for us to have this equilibrium, you want to make sure that in equilibrium, the receiver exactly chooses R star and nothing between R star and A star. Now, to get to this, what I'm going to show you is two lemmas. Now, the first part, it shows us that if this equilibrium exists for any size of the action space, it's going to exist for any smaller size of the action space. Now, what's the logic of this result? So let's start with this action space from 0 to Q. And given this action space, given recommendation R star, the optimal thing is to take action R star. Now, let's shrink the size of this action space from Q to Q prime. Now, as we shrink the size of the action space, for every path that I was making recommendation R star, I'll continue to make recommendation R star. If the path was hitting B for the first time at R star from 0 to Q, in a smaller action space, this is still going to be the first action that you are going to get B, because I'm only eliminating actions to the right of R star anyways. Moreover, if we are at event, if the realized path was this brown one, and we were getting a minimum at R star, in a smaller interval from 0 to Q prime, we will continue to get the minimum at R star, because I'm only eliminating actions to the right. It wouldn't change this point being a minimum. So as I shrink the size of the action space, all the paths that I was making recommendation R star, I'll continue to make recommendation R star. Now, what changes is that, like these paths, like this pink one. So for this pink Brownian motion, what would have happened was I would have recommended recommendation R hat. This was the best possible action I can take as the expert. But now, as I shrink the size of the action space, I can no longer make this recommendation. And now I'll end up making recommendation R star. Now this is the minimum for the path from 0 to Q prime. So that means, and this is only possible for those paths that attain a minimum above B, because if we are hitting B, it doesn't matter whether we get something here, we would have made the smaller recommendation. So that means as I shrink the size of the action space from Q to Q prime, I'm adding paths to event greater than B, and all the paths already were there, they stay. That means now the ratio of paths in event greater than B over event equals to B is increasing. So that implies that the probability of event greater than B, it's going to be decreasing in the size of the action space. The smaller the action space is, the more probable that we are at event greater than B. So basically, this is going to tell us that it's going to be easier to sustain equilibrium in a smaller action space, because I'm putting more probability to event greater than B where we are aligned and you don't want to deviate for certain. And I'm taking away probability on the case where we are at event equals to B and you want to deviate. So if the equilibrium was existing for lower probability on event greater than B, it should continue to exist for when the probability of event greater than B is higher. When we are more aligned, we are aligned with higher probability base. Now, this only tells me is that if the equilibrium exists for some Q, it exists for some smaller Q prime. I still need to show this first point equilibrium, it exists for some Q. How do I do that? It's essentially the same trick. Basically, what I'm going to do is, as I shrink the size of the action space, as I shrink this Q to a smaller number, I'm increasing the probability of event greater than B. Moreover, if Q is not too large, then what's going to happen is that this curve upwards, it's going to dominate this line going downwards. Why? Because this curve, it has this infinite derivative and it follows a concave line. So if I can put high enough probability on event greater than B, it's going to be that this on expectation is going to go above. It's going to increase. So the idea is that, okay, I can put higher probability on event greater than B. And moreover, the expectation at event greater than B, it's going to be increasing at a faster rate than the expectation decreasing at event equals to B. So if I can put them equal probabilities on expectation, I'm going to get an outcome that's above. That means on expectation, I'm getting an outcome that's worse. So in fact, this equilibrium construction, it doesn't even rely on risk aversion, because I can basically, by making the action space small enough, I can make that for every deviation, you are getting something worse in expectation. However, once we add risk aversion, so once we think about these concave receiver utilities, it's going to make achieving it easier, so it can be sustained in larger action spaces. Okay, so just to recap, this whole exercise, it tells us that in complex environments, we have this equilibrium where the expert looks at the realized relation between actions and outcomes, and they're going to point at the smallest action that gives them their ideal outcome. And the decision maker will follow under two conditions. One, if the preference gap between, if the misalignment between receiver and sender, it's not too large compared to the complexity, the variance of this environment. So if B is smaller than sigma squared over 2 mu, or the action space is not too large, which is going to help us ensure there is sufficient action alignment between the expert and the decision maker. Now, for the time's sake, I'm going to skip the comparative static, but just talk about other efficient equilibria and show how this model works, how these results work beyond Brownian motion in much simpler models. So the first thing I want to talk about for this part is that I only showed you a single equilibrium where experts get their ideal point. The broader conclusion is that in the Brownian motion, every efficient equilibria that we can study, they are going to be sender optimal. They are going to be outcome equivalent to what we identified. Why? Because if we are at an efficient equilibrium in the Brownian model, it needs to be that equilibrium action distribution, it needs to have full support. So I need to be able to induce all of these different actions. Why? Because if not, then there is this open set S of actions that we don't ever recommend. But if we have that set, that means there's positive probability that this realized Brownian path, it attains a minimum in one of these actions that I never recommend, and that minimum is weakly above B. But then, instead of whatever my strategy was suggesting me to recommend, I can recommend the minimum, this point that I wasn't recommending in the strategy, and improve the payoff for both players. That means if I'm not recommending an open set of actions for any state, that means my strategy is not efficient. Now, the second part is that, okay, then for every efficient equilibrium, we have this full support of action distributions. But if we have full support of action distributions, in equilibrium, I need to be able to recommend any of the actions that are available to the decision maker, and the decision maker would follow. But at this case, as the sender, I would just recommend my own optimal action because of the incentive compatibility. I'll just look at them and recommend what's the best for myself. So these 2 points together, they imply that any efficient equilibria we can study in this model, they are going to be sender optimal. Moreover, this equilibria I introduced, for those who are familiar to the literature, they survive all these well-established refinement concepts that refine out equilibria that only exist due to meaningless language. Basically, whenever we introduce a language with any meaning, the equilibria we have survives, and moreover, those equilibria are going to be, in fact, the unique ones that survive. Okay, now, for the last 5 minutes, I'll try to talk about do we really need Brownian motion and how our results extend beyond the Brownian motion. Now, Brownian motion, we only think of it as a tractable setup to illustrate how experts derive power in practice. But more generally, our conclusion of sender optimal and efficient chip talk, it can be supported in other environments. The key ingredient, so in the paper, we show many examples. So one is that in the Brownian motion, we established this result by thinking about this action alignment, by thinking about leveraging this fact that the receiver and sender have the same ideal action for some states. But I'm going to show you an example where the receiver and sender have different ideal actions for every state. So this action alignment, it's not necessary. The distributional properties of the Brownian motion, it being jointly Gaussian or Markovian or have independent increments, they're also not at all necessary. In the paper, we have examples that's going to weaken all of these assumptions. And finally, you might think this is an issue of dimensionality. We have a one-dimensional action space and an infinite dimensional state space, the paths of all Brownian motion. But what we show is that this is not actually a dimensionality problem between actions and state space. We show actions and state space that are discrete, continuum, higher dimensional. And in fact, we show examples where actions and state space, they are isomorphic. They are basically equivalent. Now, that leaves us the question, okay, what's the common feature then? What is the essential ingredient for expert power? And our answer is that the essential feature is that expert advice is non-invertible in these environments. That means the expert can reveal their own optimal action, but this information alone is not enough for decision maker to learn their own ideal action. Yeah. Okay. Okay. So let me give you a very simple example. Now, I'm going to give you this environment that we call the minimally complex extension of Crawford tensor bells. We are going to take Crawford tensor bell, and we are going to think about, okay, what's the smallest way, what's the minimal way we can complexify Crawford tensor bell so that we get the same conclusion. So now, for what how I'm going to think about outcomes, these outcome mappings, is that I'm going to think of them having an unknown intercept, and with equal probability for every intercept, they can be facing downwards or they can be facing upwards. So the slope could be -1 or +1 with equal probability. Now, in this environment, suppose that the expert makes this recommendation R star. So the expert is going to say, take R star, this gives me my ideal outcome of B. Now, given this recommendation, the decision maker knows that the realized mapping could be this line that's facing this line with slope -1 with probability a half, or it's this line that's going that has slope +1 with probability a half. What that means, any deviation the decision maker would make, on expectation, they are getting the same outcome, because this and this one, the downward and upward sloping line, they have the same probability. So you are getting the same thing in expectation, and you're also facing a variance. So you don't want to deviate if these two paths have equal probability. That means whenever they have equal probability, this efficient equilibrium exists. The expert recommends their ideal action, and the decision maker follows it. So it's the same equilibria we identified in the Brownian motion model, but it's much simpler. It's just lines with unknown slopes. Now, it's also interesting because in this model, players always have different optimal actions. So for this upward sloping line, the optimal action for the decision maker is R star minus B, and I'm recommending R star. If you are in the downward sloping line, then I'm recommending R star, and you know that there is this better action R star plus B. So the decision maker follows it, knowing that they are not aligned in any of the states of the world. The reason it works is that, different from the Brownian model, now the receiver faces directional uncertainty. Once given the recommendation by the expert, the decision maker doesn't know whether they should go to the right or go to the left. And this gives the expert additional power. Okay, to conclude, in practice, we see experts towering over the decision makers. In practice, in models, they have no power and communication is inefficient. Now, in this paper, we develop a novel and comprehensive framework that captures expert power in practice, and we do this so by capturing the intricacies of real-life expertise. Our main contribution is to show that when the decision makers face large information equality with the experts they are facing, our canonical understanding about communication games are completely reversed. In complex environments, experts have full power. They can implement their own optimal action in equilibrium. Moreover, communication is inefficient. Communication is efficient. Now, more broadly, our broader takeaway is that expert power, it not only comes from the expert knowing a lot, but it comes from how much information it remains private after the expert uses it. So the expert power, it comes from the ability to use information and hide it simultaneously at the same time. So that's all I have to say. And thank you for listening. I hope you are not bored from the Brownian motion pictures, but here's the last one.
Hello.
Hello.
Hi, Yunus.
Hi.
I think this paper is very interesting to me. And so I'm going to try to recap what I've learned from this. And I think it's a very important subject. So basically, it's in my understanding, it tells it explains the power of the experts, but the value of experts, and it's a dynamic. So basically, it depends on several things. The first thing is environment, because when it's an information complex environment, that actually the receiver will kind of give more power to the experts. And on the other hand, the experts actually will always consider its sustainable value, and it will determine how it communicates. So I think that's extremely interesting because, for example, it explains right now, like if it's in a economically more complex environment or downward economic environment, the companies, it will actually have to resort to more advice from the external inputs. And so that means the experts will hold more, have more value. And so that also gives them more confidence to convey the information, and rather than distort information or make it sounds like shocking, but really it's shallow, whatever it is. It's like many consulting companies do. So I think that's the key. It helps to explain the sustainable value of the experts, its relation with the receivers. So it also explains the positioning of both the receiver of the expert. Experts actually is dynamic, so it has many implications. For example, for experts, they need to learn how to continuously build their sustainable expertise, and also, so that means they need to learn a lot from the environment. So that so keep their edge. They also need to learn for example, through this process to build the other values they can provide. For example, trust. Through this process, actually they can build more trust. They can also provide other values. That's how experts build their career. Fully leverage on the time of the complexity. It's not always very complex. They are not always needed. So that's on the expert side. But I think it's also on the receiver side, like the companies, stuff like that. They actually need to learn when they need to open up to listen to outside experts, and when they have to take more shots. It's the value of the information in the background of the complexity environment, and that is the nature of this talk. It's dynamic. So I think it's cool. It's really cool. But my only recommendation is that I think you guys can motivate this a little bit better. Right now, let me give you examples. Like the doctors, I think the lawyers, they are probably very typical, but it doesn't really explain the dynamic. I think what's most interesting is the dynamic of this. Because for the most of the time, I think the doctors, lawyers, they hold information and influence power absolutely. So it doesn't matter how long, whenever we are sick, we go to seek the advice from doctors. That's like almost certain. It's not interesting enough. What's much more interesting, I think, is the thing, because we are from company, so it's more interesting to give examples of the relation between the consulting companies and the companies who hire them. That's really the dynamic, because that really conveys the value of the information, and given the background, how it plays the role, the positioning, stuff like that. I think that has great implications.
Yeah, so just first of all, perfect summary of the model. Thanks for doing the summary. I definitely agree dynamics are very important. So this model, the one I presented today, so it's still a one-shot interaction, right? I tell you what to do, you do it, and the game ends. I'm very happy that you're pointing out the importance of dynamics in expert power, because we are working on a follow-up project of this paper where we exactly consider that one. So we think about, okay, expert gives you some advice today, you take an action, you observe what happens, you get some payoff, but tomorrow you have another problem. Now, if you come back to the same expert, the information expert give you today, it's now a tool for you to use against the expert. In fact, in the dynamic model, what we show is that if we think about this relationship between, like this relationship over time, the decision maker, it's going to slowly learn the relationship between actions and outcomes over time. By taking some recommendation and taking actions, they are going to learn the outcomes and actions and their outcomes. They are going to learn this relationship. Now, because of that, unlike this model, in a dynamic setup, the expert can't use their information efficiently. If I tell you everything today, then I used all my information today, and you don't need me tomorrow when you're trying to make a decision. So now expert is going to communicate inefficiently in order to keep some of its information hidden for tomorrow. In fact, what we show in this follow-up paper is that this decision maker's ability to learn, it can make communication so inefficient that both the decision maker and expert can be worse off compared to this single shot interaction. So maybe that explains some of the questions you were pondering during about the dynamics. Right. But yeah.
So I basically I agree with you. So I see that. So basically I think it's the power, anyway, the value of this paper is really to point to the essence between the expert and the receiver and the value of the information, given the complexity of the changing environment. I think that's really the set up the right framework to think about this question. So I think you can explain this a little bit better. And I agree with you. I think this is a lasting. This kind of question has lasting value for the real world, and I really recommend you keep on working on it. I think you're going to have a long career and influence on this if you have your brand of expertise established.
Thank you so much for the nice words, and thanks for the suggestions. They're very valuable. Thank you.
Yeah. So actually, we have a question from the audience in the chat. You can look at it.
All right. So.
Okay, I'm checking.
Okay, you can read it, right?
Okay, so I think it's by Quijin. It's about, in reality, we can get advice from AIs or LLMs rather than human experts. How do we model the communication in this process? So it's an interesting question. I'm not very deep into AIs or LLMs, but I think one thing that really changes with the experts of getting from human experts and from them is how we think about the bias in those models. In the models that we study, when we think about a doctor and a decision maker, it might be more clear about what the goal of the doctor or what the goal of the person who is giving us the advice is, because you might know that, okay, the doctor is trying to maximize the profits that coming from the recommendation or minimize the duration of the treatment so they can get more person in the hospital room. So you have a more idea about, okay, the bias of the person who is giving the advice. I think one interesting thing that comes into consideration with this question is, once we think about getting advice from like these AIs or large language models, it's very uncertain about what are the biases built in these models, because they're basically black box models. And it's interesting to think about how this uncertainty about the bias is going to affect these results. So there are a couple of papers that study this uncertain bias in the classical model, but I haven't studied them in my model yet. It's only going to make the experts more powerful in my framework.
Well, I think it's just a follow up what we just talked about earlier. Basically, the essence of this paper is about the value of information. Mm-hmm. And so AI and large language models, it's just speed up this process of decomposing information. So experts have to reposition themselves to ask themselves, what am I special in the AI age, right? So because the job of conveying information, a lot of that has been delegated to the AI and the LLM. So experts have to find their new way of living. That's all it is. But there is.
Yeah, another perspective is exactly what you're pointing out. I was just thinking about just replacing the expert in this model with an AI or LLM as per the question. But another thing is what you are highlighting, which is that you can think about AI or LLM as this third party that makes the receiver know more before interacting with an expert, right? Before talking to an expert, you can make your study beforehand on these platforms, and now you know more, which limits the power of the expert, as you were highlighting. Yeah. Thank you for the question.
Okay, great. So thank you so much, Yunus, and thank you for all the active participants. You're free to go now if you have any other schedule or accommodations. Welcome to stay around and discuss a little bit further if you are interested in, discussing more. Yeah, otherwise you're free to go. We are excited to meeting everybody next Tuesday.
Yeah. Thanks for having me. It was very nice, the questions and the talk.
Thank you.
Thank you.